Hi, this is Sholay Physics, episode on the applications of the Biot law. So in the last episode, I introduced the Biot law. You can check that out in the links at the end of this video. Here we have a segment of a conducting wire. Positive side, negative side. These might be connected to a battery, something like that. So the current flow is from the bottom to the top. Using the Biot law, also the equation we looked at for the magnetic field about a moving charge. It has this V cross R for the moving charge, or in this case, DL cross R hat. And this gives us the direction of the magnetic field. So applying our right-hand rule, hold your thumb up, that goes in the direction of the current, and curl your fingers around. That's going to tell you the direction of the magnetic field about the wire. So in this scenario, the current's going up this way, and we're looking at a point over here. So the direction over here where your fingers are pointing on this side is downward, okay? Underneath the wire, the field would be going to the left. To the side of the wire, the field would be going up out of the page. And on top of the wire, the current going that way, the field would be going to the right. So it has this kind of swirling pattern. The magnetic field doesn't swirl, but that's the direction of the field at those different points around the wire. So to sum it up, we have a magnetic field going into the page right here. And this location, not to be confused with the end of the page magnetic field direction, but this location is a position X to the right of this segment of the wire. And just to make sure you see this isn't just a single segment of a conductor. It is connected, let's say, to a battery over here. So there we have that segment. So we're focusing mainly on the wire itself. There's a current flow from the bottom to the top. And we're looking for the magnetic field as a function of X out here. So we are going to apply the Biot law. Just talk about a couple of pieces of this. We have the dB is a piece of that result, a piece of the B of X function that results from different segments of this conductor. So if we take a small length of this conductor DL over here, all right, it will have a impact on the magnetic field at this point, all right, and this is the vector R, and that's really important. So we see the direction of R. DL is also a vector. It is going in the up direction because that's the direction of the current. So the current is flowing along the length L, and this little DL is a segment of that. So DL is directed upward. There it is. So in a moment, we're going to be summing up the contribution of all the little pieces of magnetic field due to all those tiny little segments DL. See, there's a DL down here, a DL right there, DL in the middle. There's one last thing I need to point out. This length, the length there is 2a. Okay, so I have from this kind of a 0 point, I have the length positive a above and negative a below, so the entire length is of length 2a. So we will need the dimensions of that copper or that conducting segment. All right, so as charge travels or drifts upward in this current, each little DL will have with it a little DQ, but we are skipping past the DQ. We can use the Biot law because it's in terms of the electrical current, and that includes the little DQ. So our next step is going to be to turn this into, to put it in terms of the dimensions of this wire. So at this location, I'm going to look at this little segment. It's at a position Y above my little 0 point here. So instead of a DL, I'm going to use a DY. Okay? And we're also going to have to replace the R value. The R value is this. So it's in the according to the dimensions X and Y. we can see here that r has the magnitude of x squared plus y squared. It's going to be important there. Okay. All right, so let's replace that. Place those values in there. mu naught over 4 pi. Then we're going to have the current that's defined as I. And instead of a dl, we're going to use a dy. And instead of r squared, r is the square root of x squared plus y squared. So we will have the, I'll go ahead and write it out, square root of x squared plus y squared quantity squared. Okay, so there's one last piece where we can't ever forget. This dl cross r gives us a sine theta out there. Now that theta would be from here down to there. Okay, and that's important, very, very important. Here's our theta. As far as direction, that cross product, we've already done that. The angle is this way if we use the old right-hand rule. Angle's this way, our r is this way, so we have to curl it like that, and we get a downward into the page magnetic field. Each little segment dl, you can try it yourself. Think of a little segment dl down here, in the middle, and up here. All of them will have a downward component at that point. However, there's a piece that there's an angle here that will give us a different kind of a distance out of that. Okay, there's a little angle we need to account for. Using some trig. Lost my thought again. What's it to sine theta, and this angle isn't always necessarily 90 degrees. The amount of the sine theta isn't always going to be 1. It's not just going to be something that we can cross out here. So we do need to pay attention to what that amount is, that sine theta. So what would be the sine theta here in terms of x and y? Well, this angle is greater than 90 degrees. So if you consider the angle in here and how it relates, what would be the sine of this angle in terms of this kind of an inner angle here? So if we think about the sine function and plot that, this is sine of theta versus theta. The sine function looks like this. And this point is our 90 degrees, or pi halves. I use degrees here. This is 180 degrees. So this particular angle is greater than 90 degrees, but just a little bit greater. You'll notice that on this side and this side, they would have the same magnitude. So sine of this angle is the same as the sine of this angle in here. So the angle in here is pi minus theta, is that little angle in there. So all in all, the sine of theta is equal to the sine of pi minus theta in this instance. And this angle, because with trigonometry we can more easily work with this angle rather than one outside of the triangle. So if this is sine of pi minus theta is the same as sine of theta out here, then we can find the sine of this inner angle as being the opposite divided by hypotenuse. So we can replace the sine theta up here, writing it all out, not to miss a step, I dy over x squared plus y squared. I already distribute that little square in there. But the sine of theta is going to be x, the opposite of that angle up there in the triangle, divided by the hypotenuse, square root of x squared plus y squared. Okay, now we can combine some like terms and flesh this out a bit. dB equals mu naught over 4 pi. We'll have an I x, I'm going to bring that in there, dy, divided by, we got a x squared plus y squared times the square root of x squared plus y squared. So this is like x squared plus y squared to the 1 times x squared plus y squared to the 1/2. We're going to add those exponents. 1 and 1/2 is 3/2. So x squared plus y squared to the 3/2 power. And now we're ready to move forward. We have something that's integratable set up here, the integral of dB. So we're going to sum up all that magnetic field in terms of x. X is our variable. Excuse me, x and y. It'll be a function of magnetic field in terms of x, but we're going to sum up all the little pieces of dB that are along the length, dl or dy up here. So where will we sum that length up from and to? Our upper and lower bounds are going to be from a negative a to a positive a. So from a negative a of length y to positive a. And this is the integral we're set up and ready to do. Now if you look at this little creature here, if you try straight up like u substitution, it's not going to work. If you set this equal to u is equal to x squared plus y squared, then du would be 2y dy. And so we'd have this extra y that would not cancel with anything up here in the numerator. So that wouldn't really work for a straight up u substitution. However, you might look up here and get the hint that we did use some trigonometry. So we're going to use some trig substitution. Tangent of, and I'm going to use a new angle here just to define it. Since we have our triangle, we use the angle phi. So tangent of phi equals opposite over adjacent. So y divided by x. Here's my y in there. Can't see it, it's kind of small right now. So y divided by x. Okay, so this is what I'm going to use to substitute. We rearrange that, and I get a y equals tangent of phi times x, or x tan phi. We take our derivative to figure out what dy is equal to, and the derivative of tangent is the secant squared. So we have an x secant squared phi d phi. I just like saying phi instead of phi. It's also what Dr. Kramer used, I think that was him. Phi phi. So d phi. It's a cool name anyway. So moving ahead, I'm going to zoom out a little bit here so don't lose perspective. There we go. All right, I think we're ready to substitute a few things in here. Y is equal to x tan phi, and dy is equal to x secant squared phi. So on this side of the calculus expression, the integral, we're going to end up with a b as a function of x. Okay, so sum up all the the b as a function of x, but we still have some integrating to do over here. Oh, I'm going to not draw those in yet, just yet. I'll bring that back in. So leave the a's out for now. We're going to have a mu naught over 4 pi. Those are constants. X is a constant at this point. Okay, so it's not changing. And also, so is I. So I have an I x. I'll leave that as a term out front, kind of as a coefficient. Next, we're going to have, instead of an x dy, instead of a dy, we're going to have x secant squared phi d phi divided by, all right, in here x is still x, so we're going to keep it as an x squared. And instead of y, we're going to have a tan, x tan phi. So y squared would be x squared tan squared phi. And all that's to the 3/2 power. Looks kind of ugly so far, but things are going to work out for us here. Let's move ahead. B of x. Now I'm going to pull that coefficient out in front. U naught I x. You know what? I have an x here also, so we now have an x squared of 4 pi. All right, and we've got an integral of secant squared phi d phi. And the step I'm taking here is we've got an x squared plus x squared tan squared phi. Now if I factor out an x squared from that inside of this 3/2 power thing here, then we'd end up with a 1 plus tan squared phi. And the beautiful thing about that, maybe your eyeball's picking it up, is think of it like sine squared plus cosine squared equals 1. You've got that trig identity. Well, here's another trig identity. 1 plus tan squared phi is what? Secant squared phi. Okay, so little trig identity here. 1 plus tan squared is equal to secant squared. That's a trig identity. All right, so substituting that in, sorry about that, there's the trig identity. Okay. Now I see my x squared's over here, and it's probably going to come out with this 3/2, so I'm going to just pop this x squared back in to the inside of the integral before I integrate. X squared secant squared phi d phi up top. And on the bottom, we're going to have an x squared times secant squared phi. Can't forget that that's to the 3/2 power. Okay, and this is my ugly integral sign. There we go. Moving up a little bit. Take that in a little. We're going to distribute. We're going to apply this, not distribute. We're going to apply the exponent. That's a little prettier. And x squared to the 3/2 is x cubed. And secant squared to the 3/2 is secant cubed phi. Now I hope you see where we're going with this. We get some cancellation going on here. X squared. Get rid of 2 of those x's on the bottom. And the secant squared reduces down to 1 over x secant phi d phi. So this significantly improves our situation. And 1 divided by secant is cosine. And we can't forget that x on the bottom. Okay, now this turns into a much better situation for us, doesn't it? Now let's take that integral and bring it back out. because that is very integratable. X is a constant, so we don't have to worry about it in the integral. And we have a b of x equals mu naught I over 4 pi. And the integral of cosine is sine. So we get a sine. I'll bring that x out also. 4 pi x. Sine of theta. And we can't forget we just integrated here. So I'm gonna put my bar out here. Just to remind myself, I gotta still apply that integration. But then we get a mu naught I over 4 pi x, and sine of theta, or sine of phi, we should go back to that. Sine of phi is the same as the opposite divided by the hypotenuse of this triangle, okay? So we get a sine of phi out of it. All right, so sine of phi is the opposite side, the y, divided by the hypotenuse, which is square root of x squared plus y squared. And now we can bring the a's back into it, where a y goes from negative a to positive a. Okay, so I didn't want to put those in here when we still had phi. I'd have to, that'd just be kind of a waste of time. All right, so let's apply that. We've got I over 4 pi x times. All right, now we're going to have an a up top over root x squared plus a squared minus an a negative a over square root of x squared plus negative a squared is positive a squared. So just leave that as positive a squared. So you see this is going to be a minus a negative will give us a 2. So we'll have a 2 mu naught I over 4 pi x. And I brought the 2 out already. So the only thing up top is we're going to have an a over root x squared plus a squared. So this plus another one is 2 of them. There's the 2. And it simplifies down to this. Actually, we can do one more step of simplification. Get rid of that 2. Okay. So we end up with mu naught I a over 2 pi x root x squared plus a squared. That's the magnetic field at that point. Double checking, looks like I have it. So this is for a very finite length of wire or of conductor. Okay, finite. So what would happen if we brought our position x, zoom in here. What if we brought this position closer and closer and closer to the wire? When that happens, x becomes much less than a. When x is much less than a, we have essentially an infinitely long wire. It's kind of like walking up to a wall and putting your face against it and looking along the length of the wall. It looks really long. But if you back up, you can see the size of the wall. Right? But up close, when you're really close, things look like they're infinitely long. Okay, it's kind of a thing for you flat earth people, saying that the earth isn't round. Just when you get close to a round object, really, really close, it looks infinitely long and flat. But you got to have a universal perspective. Open your mind a little more, okay? Don't be so closed-minded. But this isn't a commentary on social stuff and religion or anything like that. I'm just saying that it applies here. When you bring a position close to this wire, x becomes very, very small compared to a. So let's apply that. When, zoom back out here. When x is much less than a, okay, what happens? Our b of x its magnitude, becomes mu naught I times A divided by 2 pi x. But this is where the term changes. When x is much less than A, then imagine, x being 1 and A being 1,000. Okay, what's the square root of 1,000 compared to the square root of 1,001? It's essentially the same thing. So if A is much greater than x, then the x kind of disappears a little bit. Mostly disappears. It's negligible. So we end up with an A squared on the bottom. And just to keep this as clean as possible, in the end, our bx becomes mu naught I. A divided by square root of A squared is 1. They cancel out. And we end up with a 2 pi x. So look at that. That's a whole lot simpler than this, would you say? And it's very practical. What we have here is an infinitely long wire. Or close to a finite wire. Okay? That's the practical application. When we're close to a wire and there's a current I passing through it, we plug in the distance, how far we are from that wire. Okay, it's got to be close. All right. So as long as if the wire is like 20 centimeters long, as long as we're like a millimeter away, this works really well. It applies. Okay, so we plug in a millimeter, the current passing through the wire, and this would be the magnetic field magnitude right near it. Of course, you have to use the right-hand rule to figure out the direction around it. So it has a lot of practical applications. And one other little point, I like looking for patterns and similarities. You might recall back from our electric field calculations that the electric field near a conductor. So again, where x is much less than the size A. What was that electric field along a length of a conductor? You might recall that it was the linear charge density lambda, the Q divided by the length, divided by 2 pi epsilon naught x. If you look at those two and their similarities, you've got the magnetic constant up here, you've got the electric constant there. Remember, one's kind of up top, like the mu naught over 4 pi, and for the electric field, it's 1 over 4 pi epsilon naught. So they have that same relationship there. But we also have the 2 pi. We have the charge along the length. This is the charge flowing along the length, and x is the distance. So they both have that same exact format, same exact form. So this is one application. Next one, I'm moving on to a current carrying loop. So that's our second application. If we have a loop, this has a lot of practical applications as well. That one will be a little bit, actually a lot faster than this one. All right, now we're going to look at a current carrying loop in the magnetic field that's at a position somewhere along the axis coming out from the middle of that loop. So anywhere along this in the x direction. This loop has a radius little a. We're looking at a position x. And it's a difficult perspective here. I have this loop kind of coming out of the page and into the page. Track a wire to connect to the positive side of the battery. And this part of the loop would be in the foreground above the page. And here we're going into the paper right here. And up top, we're going to come out. Okay, so we're going to have an in going into the paper there and out of the paper over here. Just so you can see that direction, I'll say the current is in and the current is out. All right, so we have the flow going kind of into the page here, traveling up and coming out and back to the battery over there. All right, so here's the direction of our current and our flow. All right, I hope that's good enough for that perspective there. All right, the magnetic field we're looking for is at this position. So by the right-hand rule, we're going to take a current coming out of the page here. So I'm going to back this up a little bit. So out of the page over here would give us a magnetic field kind of going this direction on this side where the wire, the loop comes out. And let me be specific. I'm looking at this little segment at the very top. Okay, that little segment right up there where the wire is coming out of the page, out of the plane of the page. What direction is the magnetic field over here? So if I take my thumb coming out of the page at that point, then over here at this position, if you draw kind of a big circle, I don't want to draw on this paper because it'll kind of muddy it up. Draw a big circle here. The magnetic field is going to be tangent to that circle, tangent or perpendicular to the radius at that point. Okay, zoom that in because it's difficult to see in this video. All right, so if this is r, let's take a distance r, and a distance r from that little segment, this little dl up here, and this is r, there's a little dB, piece of that total magnetic field going off in this direction. All right. Likewise, at this point where the current's going in, there's my thumb going down, the current's going in, then over here the magnetic field's kind of going at an angle like this. Also, if you can imagine a circle extending out with a radius r, that magnetic field would be perpendicular, that piece of the magnetic field would be perpendicular to that r. All right, so we'd have a couple of dBs here. This would be from the bottom, little dl, and this one up here would be from the top, dl. Now, what do you notice about those two directions? Well, they both have components to the right, but they would also both have equal but opposite components in the y direction, in our y direction here. So by symmetry, the y components cancel. Okay, so the magnetic field in the y direction is 0. There's no y direction magnetic field here, but there is a kind of a sum, a culmination of x direction magnetic field that's pointing outward in this case. So we're going to have to come up with a component here and use some angles and such. All right, now let's talk about that angle in terms of, we're getting in terms of the Biot-Savart law. So I'm going to go ahead and write that out. It's a good place to start. You're using Newton's second law of motion. You start by writing that sucker out. You don't want to forget your M's and your A's. Okay, so you're going to have mu naught over 4 pi I dl cross r hat all over r squared. That's a Biot-Savart law. So the first thing I'm going to do is get the magnitude of this magnetic field, and then figure out the x component of that magnetic field. Because as we look at these segments going around in the circle, these little pieces dl, they all have x components going outward, but um, the what I was calling the y component here wouldn't really be a y, it'd be more like a z component for a segment of the loop over here, comparing to this segment over here, and they crisscross kind of in this plane coming out of the page. That's the way they would crisscross. But those components would also cancel, leaving only the x component. So we're going to pull that out at the end after we sum up the bits of the magnetic field as we go around this circle. So we're going to sum up the magnetic field, and this length here goes around in a circle. So if I start, let's say at this point, and start summing up the length, little pieces of dl, what's the total length that we're going to cover here? It's going to be the circumference of the circle. So we're going to sum this up from 0 to 2 pi times the radius, and the radius of the circle is a. So 0 to 2 pi a. Now another thing I'm picking up on here, and I'm going to substitute for this in a moment, but this dl cross r, what is it going to be? Well, in each case, with our dl coming out of the page, r is always perpendicular to it. R is always perpendicular. So if we consider this as the cross product being dl times r times sine of theta being equal to the vector product of the vectors dl cross r hat, then we're always going to get a 1. A sine of 90 degrees is 1. They're always perpendicular to one another. So we don't need to worry about angle in this case of the angle between dl and r hat, the direction of r. They're always perpendicular to one another. So we'll make our substitutions here and clean this up a little bit. From 0 to 2 pi a, mu naught over 4 pi, and this will be an I dl, and dl cross r is sine of 90 degrees, which is 1, divided by, so dl and r are always 90 degrees from each other. And r squared, that's going to be x squared plus a squared. R is the square root of x squared plus a squared. So r squared would be, I'll go ahead and write it out, x squared plus a squared, quantity squared. All right, let's figure out what b is going to be. So summing all the db's would give us b. And now this is just dl. We're looking at the length going around. So all of this material in here is constant. X isn't in terms of L, A isn't in terms of L. X is the distance away from the center, and A is the radius. DL isn't affected by this too. So we're just summing up the length around the circle. So we're going to have a u over at 4 pi times I, and the length around the circle, when we integrate that, is just an L. And we'll take a 2 pi a, substitute that in for L, minus 0, substituting that in for L. So we end up with a 2 pi a minus 0 after you integrate and apply those upper and lower limits there. And we still have the square root of x squared plus a squared, quantity squared, which is x squared plus a squared. Okay. So our generic magnetic field is mu naught I over 4 pi times 2 pi a over x squared plus a squared. We can simplify that a bit. The 2 pi would cancel out most of that 4 pi, leaving a 2 behind. And we'd have a mu naught I a divided by 2 times x squared plus a squared. Okay. So be careful here. This is not the magnetic field at that point. it is more than the actual magnetic field at that point, because components of this cancel out. Do you remember back up here? The y components would cancel, leaving only the x components. So what we want to do is remember that this b is a vector. We want to recall that b of y is 0. So what would bx be? That would be the magnitude of what we're looking for here. All right, so what we would have b 2x squared plus a squared times what? Let's go back up here. Well, up in this diagram, if we're looking for the x component of this little dB, all right, we're going to be summing up all those x components. They would all have the size equal to this one. You see, the size of the x component of dB would be the same as the x component of the dB from the top. So b from the bottom would be the same as the b from the top in those y directions. Okay, so those y directions cancel, but they both have the same x component length. So if this length up here is equal to a, well, actually, let's go this way. This is theta. What angle inside this triangle, of which we have dimensions, what angle is this equivalent to? Well, here's a small angle here. By my vision, it looks smaller. Okay, this angle looks smaller than this theta over here. But what we do know is that 180 degrees minus a perpendicular angle in there, so minus 90 degrees, would give us 90 degrees. And that means the sum of theta plus this inner angle in here is equal to 90 degrees. Well, inside the triangle, what two angles are also equal to 90 degrees? What two complementary angles? This inner one and this one up here. So if you work out the kind of the geometric trig ratios here with the triangles, keeping in mind that the sum of all the angles inside of a triangle is 180 degrees, then this theta over here is equivalent to this angle in here. Okay, so this angle up here. So if we want the x component, the one going out this way, that would be the cosine of this theta. All right, so the vector b has a x component coming out this way. It's the cosine of this theta. This theta right here would be equal to the x component of vector b. So I bumbled through that a bit. Shelley tends to bumble at times. But what we're looking for is the x component, or the cosine component, and cosine of theta is equal to the cosine of this one up here also, which would be a divided by the square root of x squared plus a squared. All right, so we can substitute cosine theta is a divided by square root of x squared plus a squared. I'm going to substitute that in down here. U naught IA over 2x squared plus a squared times a divided by the square root of x squared plus a squared. All right. Increase vision. So B, our magnetic field in the x direction, we're going to multiply these together. U naught I a squared divided by 2 times, and combining these two terms, x squared plus a squared to the 3/2 power. That's it. So again, looks kind of ugly, but when are we really going to use this little fact? What's the magnetic field at a point somewhere along the axis of a coil of conducting wire, so electricity conducting wire there. We don't quite use it very often when we're looking at a magnetic field outside that current loop, but we do often in physics and electronics consider the magnetic field at the center of that kind of loop. So what would happen as x decreases and approaches 0, or when x becomes 0? All right, so when at the center of the loop, x is 0. And what would the magnetic field be there? Well, the magnetic field there would be, well, all we'd have to do is plug in a 0 for x, right? So 0 for x would give us a mu naught I. Wow, I just drew an I again. I'll make that into an A squared divided by 2 times a squared to the 3 halves. And a squared to the 3 halves is a cubed, and a squared divided by a cubed would be 1 over a. So our final result at the center of the loop, we'll make a little loop there, okay? The magnetic field at the center of that loop would be mu naught I divided by 2a. There it is. Okay, another like nice simple application. If we've ever got a loop or coil, then that's the magnetic field due to a current running through that coil, and that coil has a radius a. So the smaller the a, the greater the field, the closer that magnetic that position is to the wire. That should make sense also. So one last little application. What if I've got say a coil has a bunch of loops in it? Let's say n number of loops. All right. Then what would be the magnetic field at the center there? It would just be n times mu naught I over 2a. Okay, so that's for an n number of loops. So those are our main 2 applications: magnetic field along a straight wire, and magnetic field a short distance away from a looped wire, and also at the center of that loop is mainly it. That wraps up this lesson. Whew, that was a lot, I know. Thank you for bearing with me. And guess what? There's an easy way to do all this stuff. Just like Gauss's law made your world a whole lot easier, rather than having to do all this, that, why is it? Rather than doing all that, remember with electric fields and Gauss's law just kind of simplified that. Guess what? There's a wonderful dude called Ampere, and he made a law too. So more to come on Ampere's law. It'll be coming up soon.